Hey there! You ever look at a math problem with a bunch of square roots and just think, how on earth am I supposed to multiply these things? Well, if you have, you are in exactly the right place. Today, we're going to totally demystify multiplying radicals and turn what seems tricky into a skill that's actually pretty straightforward.
So, let's just jump right in with a little challenge. Take a look at this. It looks kind of messy, right? I'm going to promise you something. By the end of this quick explainer, you're going to know a trick that makes this problem, well, surprisingly simple. So stick with me, and we'll crack this thing together.
Here's our game plan. We're going to start with the absolute foundation, the one rule to rule them all. Then we'll level up using a tool you probably already know, FOIL. After that, we unlock a secret weapon I like to call the conjugate superpower. Then we'll cover how to dodge the common mistakes. And finally, we'll see why any of this actually matters in the real world.
All right, first things first, the basic rule. This is the bedrock. Seriously, every single problem we do today, no matter how complicated it might look on the surface, it all comes back to this one simple, powerful idea.
And here it is, the product property. All this says is you multiply the numbers times outside the square root signs together, and you multiply the numbers times inside the square root signs together. Outsides with outsides, insides with insides. That's it. That's the whole rule.
So let's put this to the test. Let's say we have 3 root 2 times 5 root 6. Okay, first, the outsides. 3 times 5 gives us 15. Then the insides. 2 times 6 gives us 12. So we get 15 root 12. But, and this is a big but, we're not done yet. You always have to check if you can simplify. The square root of 12 can be broken down into the square root of 4 times the square root of 3. And we know the square root of 4 is 2. So our final move is 15 times 2 root 3, which gives us our nice, clean answer, 30 root 3.
Okay, so what happens when things get a little more complicated? When we have expressions with two parts, called binomials. Well, we don't need a new tool. We just need to reach for an old friend you probably remember from polynomials.
Remember good old FOIL, first, outer, inner, lost? It works the exact same way with radicals as it does with variables like x. So let's just apply that same 4-step dance to this expression right here.
Let's kick it off with f for first. We multiply the first term in each set of parentheses. That's the square root of 3 times the square root of 3. Now here's the cool part. Anytime you multiply the square root of a number by itself, you just get the number back. So square root of 3 times square root of 3 is just 3. Poof, the radical is gone.
Next up, O for outer. We're going to multiply the two terms on the very ends. That's the square root of 3 from the first one and negative 5 from the second. Put them together and you get negative 5 root 3. Simple enough.
Now for I, the two inner terms. We've got the 2 from the first expression and the square root of 3 from the second. Multiply those and you get a positive 2 square root 3.
And finally, L for last. We multiply the last term in each set of parentheses. So that's 2 times negative 5, which of course is negative 10.
Okay, now we just got to scoop up all our pieces and put them together. We have 3 minus 5 radical 3 plus 2 radical 3 minus 10. Now we just combine the things that are alike. So the regular numbers, 3 minus 10 is negative 7. And the radical terms, negative 5 radical 3 plus 2 radical 3 is negative 3 radical 3. And that's our final answer right there. Negative 7 minus 3 radical 3.
All right, now for the main event. This is where things get really cool. What if I told you there's a special pattern, a kind of algebraic shortcut that can make radicals just vanish? It's not magic, it's just math, and we call it the conjugate. It is a genuine superpower in algebra.
So here's the secret. Whenever you're multiplying two binomials that are almost identical, but one has a plus and the other has a minus, that's the signal. You're using conjugates. This is just the difference of squares pattern you've seen before, and look what it does. You just square the first part, subtract the second part without the square root, and the radical is completely eliminated.
Remember that puzzle from the very beginning? Let's solve it right now. We have 4 plus square root 5 times 4 minus square root 5. This fits our conjugate pattern perfectly. Here, our a is 4 and our b is 5. So we just use the formula, a squared minus b. That's just 4 squared, which is 16, minus 5.
And the answer is 11. Just 11. How clean is that? We didn't need FOIL, we didn't need to combine like terms, nothing. The conjugate pattern just wiped the radical right off the map. That is the power of this amazing shortcut.
So you've got the rules, you've got the superpower. Now let's make sure you really lock this in by going over a couple of common traps that almost everybody falls into at first. knowing what not to do is just as important.
Okay, this is probably the #1 biggest mistake. When you see something like square root of 3 plus 2 squared, it is so tempting to just square each part and say, oh, that's 3 plus 4. But that is totally wrong. You got to remember, squaring something just means multiplying it by itself. So you have to write it out the long way. Square root of 3 plus 2 times square root of 3 plus 2, and then use the full FOIL method. You'll get the right answer, which is 7 plus 4 square root 3. The other common pitfall is just getting a little lazy at the end. Let's say you multiply radical 3 times radical 12. You get radical 36. Great, you did the multiplication part right. But you're not finished. Don't stop there. The square root of 36 is a nice, clean number, 6. Always do that final check to see if your answer can be simplified any further.
So you might be thinking, okay, cool trick, but why does this matter? Is this just something for a math test? And the answer is absolutely not. This little algebraic tool has some seriously important uses out in the real world.
Believe it or not, this isn't just a textbook problem. In fields like electrical engineering, professionals use this exact same idea of conjugates to simplify really messy calculations involving something called complex impedance in AC circuits. The same trick we just used to make radicals disappear is a fundamental tool they use to make their work possible. And that brings us to a final thought. We've seen how this conjugate superpower can make radicals vanish. So what's next? How could you take this exact same superpower and use it to solve a brand new problem like getting a pesky square root out of the bottom of a fraction? Well, that's a great question and a story for next time. Thanks so much for tuning in.